Last time we made a happy little pattern matcher. There he is. Well, what are we going to do this time? Well, I suppose at some point we've got to make it all, haven't we? So, don't really matter. Let's do this bit here. But what is this bit? Let's have a look at the old paper again, shall we? So let's read this bit here. And it says each mail stop is capable of buffering one message in the outbound direction and one message in the inbound direction. So it's just the inbound buffer. That sounds simple enough to make, doesn't it? So let's have a look at the message that gets sent on the old chatter ring bus. It's got 4 categories. The first one is control. That's a bit complicated, so we'll go through that in a later video. Then you've got data. Well, that's the stuff that's being sent, so the information. The source, that's who sent it. The destination, and that's who it's for. But for our inbound buffer, we don't really need to worry about the destination, because we already know it's for this computer. So we're just left with control, data and source, which can be put into 4 8-bit registers. So let's do that. For our 8-bit registers, we're going to be using the 74HC574. Go on, human man. You get that breadboard. Yep, now get the chips. Now stick them on the breadboard. Now, do power and ground. You know the drill, human man. Now, connect together all the clock inputs. Well, I can't really see what else there is to do. I suppose that about finishes this video, doesn't it? Acne, you wee puke! You haven't read this bit. It says messages will be received by a mail stop only if its pattern matchers are enabled and deem the message appropriate, and its inbound buffer is empty. Now, get to it, or I'll give you a taste of the back of me cane. Yeah, alright, Nan, alright, we'll get it done, don't you worry. Phew, Nan's accent ain't got much better, has it? So, we got to get a message from the ring bus to the inbound buffer, just like this. And the only signal we got is this one down here, the load signal. That is the clock signal on our 74HC574s. So remember, we tied all 4 of them together, so it loads them all simultaneously. So a rising edge on the load signal, well, that loads the message into the buffer. Simple enough, isn't it? We ain't going to worry about where this rising edge comes from just yet. Just accept that it exists, alright? The only problem we got here is that every time you get a rising edge on this load signal, well, it's going to overwrite the inbound buffer, isn't it? So what we need is a magic box. Now, this box looks to see whether the inbound buffer is empty or full. So, if the inbound buffer is empty, the rising edge on the left-hand side of the box just appears on the right-hand side of the box. So, the message gets loaded into the inbound buffer. And then, when the inbound buffer is full, the magic box doesn't let the rising edge from the left-hand side go through to the right-hand side. So, the inbound buffer isn't overwritten. So let's work out what's going on in this old magic box. I mean, I guess we could probably just use a D-type flip-flop, couldn't we? Well, let's make it a bit easier and get rid of the set reset bit, because we don't need that for now. Now let's say when the inbound buffer is empty, we stick a 1 on the data line of the D-type flip-flop. And the load signal, well, that's just the Q output. So when we get a rising edge on the clock, we get a rising edge on the load signal. And when the inbound buffer is full, well, we stick a 0 on the D input. The first time we clock the flip-flop, we'll get a falling edge on the load signal. But the load signal, we don't care about a falling edge, so it doesn't do anything. And then the next time it's clocked, well, it's just a 0. And every time you clock it, it's just 0. So the load signal, well, it's not doing anything, is it? Which means the inbound buffer won't be overwritten. Now we just need to generate this empty full signal. This is what we come up with. We bunged another flip-flop up here and we put the empty signal going to the set line on the second flip-flop. But how do we know when the inbound buffer is empty? Well, it's actually quite easy. We know it's empty when it's been read. And it's read when the output enable line on the 74HC574 goes low. So we can get rid of this empty signal that we don't know what it is and change it for the inbound buffer read signal, which we know is active low. Let's just quickly go through how this circuit works. So to start with, the read signal, well, that's high or inactive. So the Q output of the top flip-flop is 0. So when the bottom flip-flop is clocked, we just get a 0 on the load signal. So that doesn't do anything. When we read the inbound buffer, we put a 0 on the read signal, which sets the flip-flop. So we have a 1 on the Q output of the top flip-flop. And now, when we clock the bottom flip-flop, we get a rising edge on the load signal. But we also get a rising edge on the top flip-flop, which, because the data input is just tied to ground, we get a 0 on the Q output of the top flip-flop, which means every time we clock this bottom flip-flop now, we just get a 0 on the load signal. So there we are. We've done it. We can tell when it's full and when it's empty. You ready to build it, human man? Stick some power and ground on there. Now, get that 74HC74. Now add power and ground to the chip. Now start connecting up the other signals. Test it, human man! So, the human man has built a little circuit to emulate the read signal and the clock signal. Show him, human man. Yep, that one does the read signal. And that one does the clock signal. There's an LED on there as well. We'll point to it, human man. That LED shows the load signal. So, switch it on and see what happens. Now, let's clear it all. Now, when we press the clock, no matter how many times the human man presses it, the load signal doesn't come on. But if he does a read first and then clocks it, oh, and then he presses it again and it goes off and it stays off. Oh, what you done there, human man?
Are you going soft in the head or something? Oh, the idiot.
There's a big problem with this circuit. Have you figured out what it is yet? The problem is, it don't work. God, imagine if we just spent the last 5 minutes explaining and building a circuit that don't work. We'd look like a right couple of idiots, wouldn't we? You see, the problem is, if you read the top flip-flop before the bottom flip-flop is clocked, we end up sticking a 1 on the input of the bottom flip-flop, and when it's clocked, well, the output just stays as a 1. And then every time it's clocked, it just stays as a 1. So it just stays latched. Yeah. I suppose we better change it, haven't we? To fix the problem, we come up with this circuit. And as you can see, it's a lot simpler. It's a circuit we should have made in the first place. But for some reason, we made that other monstrosity, didn't we? Anyway, let's just go through how it works. So to start with, Q is low. Then we're going to clock the flip-flop, and then we get a rising edge on Q, which obviously gives us a rising edge on the load signal. Now Q stays as a 1. So every time we clock this flip-flop, well, the output just stays as a 1. And all the load signal cares about is a rising edge. So if it just stays as a 1, it don't matter. And then when we read the inbound register, we reset the flip-flop. So then, the next time it's clocked, we get a rising edge again. It's way simpler. Don't know why we didn't just do that in the first place. This circuit has the added bonus that it blocks the load signal while the inbound register is being read. So the contents of the inbound register can't be changed partway through a read cycle. It's such a simple circuit, but the human man's built it anyway. So let's test it just to make sure. So, do the read signal. Oh, now clock the flip-flop. And again. Oh, and then when you read, it goes out. Now human man, press it again. It works, human man! It works! So, where are we going to get this read signal from then? Well, originally, I was going to use this monstrosity of a circuit here. So, every output enable on the inbound register gets fed into this 4-input NAND gate here. And then, the output of that gets fed into the clock of this counter. And once this counter is counted all the way up to 4, it pops out a read signal. The problem with doing it like this is that it limits the system, because it means you have to explicitly read every single register. And we might not want to read all of them, because we might not care about the whole message. So what we're going to do is, we're going to bin all this and just take our read signal from the output enable line of the data 1 register, and then just handle the rest in software. Now this has the added bonus that we got less chips on here, so it's cheaper. You probably also noticed that we changed this bit to this bit, and that we got this thing up here which is unconnected. Now this comes from the pattern matcher, and also some other stuff that we ain't gone through yet. But we won't connect it all up just yet. We'll save that for a future video. I reckon that'll do for this video, don't you? I reckon next time we could probably have a go at doing some decoding. That'll be nice, wouldn't it? So, yeah, bye. Bonk!
Let us watch as Jeff flies majestically in his portable toilet, propelled by nothing less than his own torrential diarrhea.